So indeed, half of my talk will be dedicated to our recent updates on the code we've been working on called Entity. So that would be dedicated to the actual name of the session. My first half will be more of a transitional from the previous session yesterday, where I'll try to give an example. I pick one particular case study as an example of what goes wrong in our understanding of classical plasma physics, laboratory or space plasma physics, when you tune the parameters to their extremes. To sort of establish a ground base of discussion, let's talk about briefly what goes wrong or what goes right, if you will, when you consider plasmas not around our household or more familiar environments, but rather go in the surroundings of neutron stars and black holes. In these environments, oftentimes, instead of having normal matter, the plasma is dominated by electron-positron pairs, most of the time produced right there and then. Involved energies are oftentimes much greater than the rest mass of electrons and even ions, in which case you are dealing with ultra-relativistic plasmas. And quite often, the magnetic field strength is so strong, the magnetic field is so strong that the magnetic field energy density is often much, much greater than the rest mass energy density of the plasma. And typically, we talk about these so-called sigma or magnetization parameter, which in many of the instances is much greater than 1. In some cases, for instance, in the cases that we talked about yesterday around magnetars and regular pulsars, the involved magnetic fields often exceed or come very close to the so-called Schwinger limit, the QED limit, of about 10 to the 14 Gauss. And another thing that was mentioned yesterday by Chris is the so-called compactness parameter. Chris mentioned this in the context of luminosity of an object, but oftentimes the involved dissipation involves magnetic fields, so we oftentimes just plug magnetic field there and call this LB. And this parameter essentially tells you that whatever dissipation process you have operating in the system, whatever energy is released is radiated away in situ, so within the system, within the light crossing time of the system, which is how we observe these objects in the first place. And typically there are different ways of extracting this energy, most of the time magnetic energy, sometimes kinetic energy. So there are different ways of extracting, tapping to that energy reservoir. There is direct acceleration by the electric field, just like in near the polar caps of the neutron stars. There's magnetohydrodynamic turbulence. Collisionless shock to extract kinetic energy of the flows. And in particular, we will be focusing today on the magnetic reconnection. So this will be a case study of magnetic reconnection when you go from laboratory-like parameters to the extremes. So reconnection itself was discovered to operate near the surface of the sun in the so-called solar corona. And so some of the parameters that we know about it are that it's very efficient in releasing the magnetic energy. It operates at a fraction of the Alfvén speed, so about 0.1 of the Alfvén speed. And of course, near the sun, it's happening in the hydrogen plasma. Now, near the neutron stars and black holes, like I mentioned before, it's most of the time we're dominated by the pair plasma. The Alfvén speed approaches the speed of light if this magnetization parameter is large enough. And thus also the available magnetic field energy per particle is large. What this means is if you release that energy, inevitably you go into the relativistic regime. As it turns out, the evolution of this system, so this is approaching two approaching regions with magnetized regions with opposing polarities. The dynamics of it is highly nonlinear, so you form what's called magnetic islands, and in between the magnetic islands are small regions where the actual release of the energy takes place. This is where the J dot E, the ohmic term, is non-zero. And it turns out that this process is also very efficient in relativistic regime, is very efficient in accelerating particles. So forming power laws in relativistic reconnection is actually quite simple. So this is one example of what the energy distribution looks like in the pure plasma two-dimensional reconnection. The characteristic energy to which you accelerate the particles, unsurprisingly, has to do with the sigma parameter, with the magnetization parameter, which, as I mentioned, simply evaluates how much energy you have available per particle. Now, the dynamics of particles is also very interesting when you go to 3D. So in the two-dimensional picture, so this is a slice, a series of slices at different times following a single particle trajectory in a three-dimensional simulation. So the particle starts somewhere upstream. So the region far from the current layer is oftentimes referred as upstream. It follows the magnetic field line because it's very magnetized. The Larmor radius is microscopic. It enters the X point. So here we plot the gamma factor, and the vertical axis is time, which points downward. So as the particle enters the X point, it gets the direct acceleration from the unscreened electric field. After that, it gets advected. So as you see, the particle's energy grows all the way up to sigma. So it gets advected by essentially a magnetic field line. But the story doesn't stop there. So as it turns out, then this was a process discovered quite recently, that in 3 dimensions, particle is not getting trapped inside the plasmoid. It actually has a chance to escape the trapping. And this has to do with the structure of plasmoids in 3D. I'm not going to stop too much into that. But essentially, after the particle is released from the layer, it undergoes this so-called secondary acceleration in the converging flows. So essentially, it's an E cross B motion where the magnetic field also switches its sign. What that means is you can have trajectories where your particle's motion always points along the electric field. And if that's the case, the electric field does work on the particle, and there is basically a direct acceleration. So this is what that motion looks like in 3D. And again, this is a process which operates only when you do this in 3D. With the help of this process, you can accelerate particles much greater than sigma. Now, to be clear, the mean energy will still be smaller than sigma. So the power law cannot extend, the -1 power law that I showed before, gamma to the -1, cannot extend further than sigma because you have energy limit to obey. So it's going to be much steeper power law, but nonetheless, as I'll show for the radiation purposes, so for the purposes of extracting energy, that's still quite a lot of energy. Okay, so this is all with very vanilla, no radiation case. So what happens when you actually consider realistic parameters where the radiative drag, the radiative reaction on these particles is actually strong, which is the case in the environments of neutron stars and black holes. So the story actually changes quite drastically, and the system becomes more similar to the two-dimensional case. So the way we parameterize the radiative drag is through this so-called gamma rad parameter. This parameter essentially tells you the gamma factor of particles for which the work done, or the force of the synchrotron drag is comparable to the work done, or the force of the electric field, of the reconnecting electric field. So this is a fiducial parameter, if you will. As you see, it doesn't include any of the angle dependency. So this gamma rad parameter has a beautiful property in that it only depends on the magnetic field strength. So in other words, if you know a magnetic field of a given astrophysical system, you right away know this gamma rad parameter, so you know what the characteristic Lorentz factor of particles is at which it becomes radiatively dominated. So the jargon is that we call strong cooling regime cases where this gamma rad parameter is smaller than sigma. Because sigma is the characteristic energy to which you accelerate particles. That means particles become radiatively dominant before they reach this sigma limit. Now, does that mean that particles don't go all the way to sigma? It's actually not the case, especially for the reconnection, simply because in the reconnection, the acceleration happens in regions where there is no magnetic field at all. So particles can still reach sigma, but what this formula tells you, what this strong cooling regime tells you is as soon as they hit this limit of sigma, in this case, so particle at this point is at the edge of the exhaust, it has energy of about sigma, but as soon as it reaches a region where it sees the magnetic field, it catastrophically cools down and is basically trapped inside the plasmoid. So in that regard, this dynamics is more similar to the two-dimensional reconnection than the case without cooling. So this is what it looks like, the close-up view of that. Now, another beautiful property of this parameter is the fact that the peak energy, the peak synchrotron energy associated with this gamma rad parameter is actually a collection of fundamental constants. And if you've ever opened Rybicki-Leitman, this number is actually 160 MeV. Now here, there is an additional factor, because in Rybicki-Leitman, you're simply taking the magnetic field here as a measure. Here we're taking the electric field, which is 10 times smaller than the magnetic field, because we know what process does the acceleration. And in reconnection, the electric field, the resistive electric field, is about 10 times smaller than the magnetic field. So which is why you have this additional factor here. So for electron positrons, this number is 16 MeV. What this basically means is that if you have a collection of particles in the radiatively dominated regime, you inevitably radiate synchrotron photons at 16 MeV no matter what. What does the spectrum of these photons actually look like? So this is the distribution of pairs in such strong cooling regime. As you can see, you form a very hard power law gamma to the -1 all the way to this gamma rad parameter. But after that, you enter the cooling regime, so you have a cooling break, and after that, you still have particles that reach sigma because of what I mentioned before about the acceleration in the x points. But there is far less energy in there. So if you transfer this, including all the angles, et cetera, if you transfer this into the emitted photons, this is what it looks like. So the peak of the emission, where most of the energy lies, is somewhere around 16 MeV. But then you have a tail, and the properties of that tail might depend on all sorts of different things, such as the beaming of the plasma. It's sensitive to a lot of the details of the system, but basically you have a power law tail which extends to this limit of gamma rad divided by sigma. Now, if you're attentive, you might notice that if you naively extrapolate, this has to be squared. There are reasons why this is not square, and it involves thinking about angles. And if you're interested, I can elaborate more, but I'm not going to talk about that too much. Okay, so if your gamma rad is, say, 100 times larger than sigma, that means you will have some component of it in the gamma rays, in the GeV gamma rays. But in that regime, it's actually very hard. We haven't been able to explore that regime numerically, so it's very hard to extrapolate it to those scales where you have sufficient emission beyond the GeV. Okay. Now, what happens if you add ions? So this is going to be a discussion of mostly pair-dominated flow. So it's pair-dominated plasma undergoing reconnection, but then you add a pinch of ions. The ions, in principle, their dynamics does not really depend on the mass ratio that you put in numerically. Because what matters is the product of the energy, or gamma times mass, which will essentially adjust to whatever mass ratio you put in. So we explored the parameter regimes up to, I think, 20 or 16, it really doesn't matter. So in the simulations I'm going to show, we're taking the mass ratio of 5, I think. But what's important is that ions are not cooled. So these protons or ions, I'll use these terms interchangeably because these are still fake particles. So these are essentially positrons, but without cooling. They have some mass ratio, but that's not relevant. So this is what their dynamics looked like. The solid lines are the pairs, the distribution of pairs, and the dashed lines are the ions. This parameter, the color, basically indicates how strong the cooling is. So the blue one is the strongest cooling. The red one is basically no cooling. When you have no cooling, the dynamics of ions and pairs is essentially identical because they're basically doing the same thing. But if you turn on the cooling for the pairs, what happens is that pairs are now limited by the gamma rad. So this is where the gamma rad roughly is. But ions don't care much about gamma rad. So their dynamics is fully decoupled. And in fact, if you look at the volume rendering of such a simulation, this is what it looks like. So the red here is where the pairs are. And then the ions, which have much larger energies, they actually form this cloud around the reconnecting layer. This is just an outline of what the trajectories of both the electrons and or pairs and the ions look like. I'm not going to step too deep into this, but basically electrons ultimately get trapped inside the plasmoids, whereas ions, after the direct acceleration, they escape and they undergo this secondary acceleration in the converging upstreams. Now, how far can you go? How far can you blow this bubble? Well, the answer is actually, at some point, ions have to start speaking with the magnetic field. So they have to establish an equilibrium with the upstream magnetic field. And this is what we're seeing basically here. This is the pressure tensor components in the z direction, so basically across the layer. This is force balance, essentially. So within the layer, the pressure is dominated by pairs, which, to remind you, are hot or are very cold because you release the energy, you put it into pairs, and they radiate it away right away. But then as you move further, the pressure is actually now controlled by the ions, which are streaming without even noticing pairs. So this is roughly the scale height of the ions. And so it's literally a cloud, an atmosphere of ions on top of the thin, cold layer. So the characteristic energy to which you can accelerate the ions is dictated by this sigma ion, where you take the sigma and instead of the number density of pairs, you plug the number density of ions. In this case, because ions are subdominant in the number, this value is much larger than the sigma. And this is what the spectra of these ions looks like. So the dashed in this case are the pairs, and the solid one is ions. And this is, again, two simulations with different cooling. And as you can see, if you increase the cooling, of course, pairs fall back, so the energy of pairs goes down. However, ions don't seem to care too much because they essentially speak directly to the magnetic field without the mediation of ions. Now, I would put the independent of electrons into quotes because there is actually a feedback going on here. Because if you suppress reconnection, you will stop accelerating ions. If you stop accelerating ions, this is relativistic plasma. So the Larmor radius is gamma times the ion, gamma times the ion mass. You will essentially deflate this bubble. So there is a feedback going on. So ions cannot fully suppress reconnection, but they just simply establish some sort of an equilibrium. Now, I am not going to stop too much into this, but we think that something like this might be operating around the M87, the supermassive black hole in the M87, where in the global GRMHD simulations. We've observed episodic explosions where you form magnetically reconnecting current layers. And observationally, so the dots here are the observations. The lines here are basically reconstructed synthetic spectra. Observationally, we see this process going on from several decades in energy, from a few hundred of MeV all the way to TeV. You should take these observations with a grain of salt because these are integrated at different timescales. TeVs are actual detections of a flare itself. So in other words, these happen at the scale of few days, whereas the Fermi data, the GeV data here, is actually integrated within a few months. So we think that this lasts for this episodic flare that we observe lasts for a few days. So if you integrate it with a few months, inevitably you're going to take some of the quiescent state as well. So the spectrum of the actual flare itself is most likely higher than this. So because of that, you should take this with a grain of salt. But this is sort of the outline of how we think this kind of effect can be actually observable. So there are different components to this emission. Okay, so I will stop here and take some time from my questions time to take questions on this, because I'm going to change gears in the next. So if there are any questions, Alex.
So you said there's acceleration beyond gamma ray.
Yes.
So you said that numerical resolution or scale separation doesn't allow you to look at that. But can you speculate whether you can achieve a power law above that?
Sorry, what do you mean?
Can you speculate whether you can achieve a power law above gamma ray? Because right now it's not conclusive, right? Whether you have a exponential decay or a power law.
Well, no, well, it's... Can you repeat the question? Yeah, so the question is, if I understood correctly, if the dynamic range between gamma red and sigma is not large enough, it's not conclusive whether there is a continued power law beyond it, or whether you can fit it with an exponential. You cannot fit it with exponential, first of all. It's still a decade in energy, so that's for sure. Now the question, to explain the complication why we cannot push the strength of cooling even further down, is because when you push the strength of cooling, you actually remove the pressure from the plasmoids. Plasmoids essentially collapse. At some point, your densities involved become so large that you stop resolving the skin depth. So you have to, have some sacrifice on how strong you can put the cooling in. But it's still a decade in energy. So we went about gamma red to sigma of 0.1. You're right that in realistic parameters, it actually might not be too far from that. So in realistic parameters, we don't know what the sigma is, but it's unlikely to be much greater than, say, 100 times. So another decade. There are systems where this, in GRBs, for instance, there are systems where this might be like 10 to the minus 6. And then I agree the dynamics might actually be quite significantly different. But here, it's not that different.
If you look at the spectrum all the way up to TeV, 10 TeV, so it's not easy to see from here, but it's more or less a single power law from let's say...
This?
No, actually, that is way above, above the... So between 10 to the 5 to 10 to the...
Oh, this?
Yeah, and above, during the flare, it's actually quite high. Yeah, those ones.
This one?
Yeah.
These are different flares, by the way. This is not a single event, but yeah.
Yeah, I understand. But so what I'm trying to say is that you need at least a power law that goes through that amount of energy range.
Sure.
To get something like
this is 2 decades in photons, which means it's a decade in energy and particles. It's not much. Okay. Okay. if there are no questions, I'm happy to take the questions about this section also afterwards. So I'll just move on. All right. So changing gears and talking about numerics. So all this beautiful progress that we've made through the past decade or so, I think would be largely impossible by many of the simulation tools, which are really, I would highlight this, these are tools that we've built in the years. So we've come a long way from simulations involving few thousand particles, from localized simulations all the way to now global billions and trillions of particles simulations on largest supercomputers in the world. And in fact, if there is anything that definitely is common between the community of astroplasma physicists and the lab plasma physicists, is exactly how much we rely on numerical simulation, in particular on simulations with using particle in cell. How much of the progress in our fields actually relies on this. So some of the challenges that we in the 2020s have with the simulations of the global systems, I tried to separate them into two categories. So first of all, there is a problem of scale separation, especially when you're trying to simulate global magnetospheres of neutron stars and black holes. So just to give you an example, the system that I was just talking about, the M87 star, the size of the black hole itself is just about the size of our solar system, so about 100 astronomical units, whereas the size of the layer that that was involved, depending on how you define the layer, but if you define it in terms of, say, the skin depth, is roughly the size of California. So it's about 1,000 kilometers, give or take. And the involved timescales are days versus milliseconds. But it's not just about the scales of the spatial and temporal scales, it's also about the scales of the magnetic field. So if you're talking, say, about the magnetospheres of neutron stars, and you're trying to model it in multiple decades in distance, you go from about 10 to the 12 Gauss magnetic field at the surface to about 10 to the 6 Gauss, this is parameters for the Crab pulsar, 10 to the 6 Gauss near what's called a light cylinder where the wind is formed. So in other words, you're also going multiple decades in the magnetic field strength, which also means you're going multiple decades in the Larmor radii of particles. So if you're trying to model these parameters, you have to either do something smart about it or reduce this separation of scales. And another important problem that we've just started to realize just recently is how much the radiative effects and the QED effects, which Alexei was mentioning yesterday, how much those actually dictate the behavior. In many cases, they do dictate. It's not just corrections and small prefactors that we can observe. They actually do dictate the behavior of the entire system. Well, for pulsars, we've known this for forever, because that's the QED cascades is how pulsars get their plasma, but it turns out that around black holes themselves, it's also very important. And this is just one example of how, if you involve some of these fundamental processes, such as pair production, annihilation, Compton scattering, etc., it entirely modifies our understanding of what the MHD, or in this case, kinetic turbulence looks like. So this is more or less a state of the art of what we had from the point of view of computational capabilities. I apologize if I did not include your favorite code here. I tried to be very inclusive, but I might not have done a good job. So apart from the very normal conventional algorithms that we know and love, there's been attempts also to include the radiative drag, the single body QED process, which are what I call single body QED processes. These are basically you track single particles and they interact with some prescribed background, so there is no need to actually couple particles together. And as opposed to the multi-body QED processes, what Alexei talked about yesterday, where you have, say, gamma-gamma pair production or even pair annihilation. So these have been included in modern astrophysical PIC codes in multiple of them. We've also had some success in modeling this whole thing in non-Cartesian geometries, such as spherical and even cylindrical geometries with logarithmically spaced grids, etc. And even there is success in including general relativity, which turns out is vital if you're trying to model environments around black holes and ask questions about how the jets are launched. And also, now we also had codes that run on GPUs, which turns out is going to be very important in the coming decades when all of the largest computers are pretty much going to be GPU-based. Okay, so, and we've had quite a lot of success with this in the past decade. This is just a subset of all the beautiful simulations that we've done and all the results that we've gotten through this. But as I highlighted, there are two, and here I added another one, challenges in this fast progress. So the two I've already talked about, but the third one I think is very important, is the usability, because if your code runs twice as fast, but your student, postdoc, etc., spends about 2 months to set up a problem, it really doesn't matter how fast your code runs. So having all of these challenges in mind and having all of the requirements of modern PIC codes in mind, a few years ago we started developing this new tool called Entity. And I want to highlight that this is really a community-driven project. So the hope is to actually make these the standard, the Athena of PIC, if you want. So this is just an outline of what we already have in the code. It's actively being used by people in the community already. So it's fully coordinate agnostic. You can put your favorite metric, and as long as you adjust the boundary conditions properly, etc., it should work. So all the solvers are written in the covariant form. We've extensively tested it on whatever cluster we had access to, and this involves some of the largest machines here and in Europe, the Frontier here, Lumi in Europe. We also tested actually on Aurora, the Intel machine that is coming online in Illinois. We also have quite extensive wiki, which also includes all the instructions how to set up the code and start running it on any of these machines. So we have all the conventional PIC algorithms, all your favorite conventional PIC algorithms that you like and that you want to use. Plus we have some of the advanced stuff already. The QED processes are still not there, so we're still working on adding them. What's important also, this is the part which addresses this usability issue. There is a dedicated library that helps you to actually analyze the data, and we try to make it as usable and as easy to access as possible. There is a dedicated Slack channel, so you're welcome to join. It's fully open. There are weekly meetings on Monday, 12 p.m. New York time. Please join. We try to help people who are just starting, and you'll be surprised how many people actually do join this. And this slide is my second to last, I know. So I just want to highlight that this is a community-driven project. If you take this code, run it, it's your code. There is absolutely no requirement on including any of the developers or any of the people who are involved in the development of the code. You're welcome to do so, but there's no requirement. It's your code. So it's fully open source, and you're also encouraged and welcome to contribute to the code. So I really want to highlight that this is an attempt to really build a community around the code rather than the other way around. Okay, so I'll not stop too much into this, and this is the plans of the development basically for the coming about half a year probably, or a year. These two things, the generalized field solver, the so-called Blina solvers, which have better numerical wave dispersion properties, etc., and then the high-order particle shape functions. These are already done. We're testing it and doing some scalings with it. So this will be pushed within a month or so. And then these are the plans, adding the QED and the sort of crown jewel of the development. And the ultimate goal is to do the so-called cubed sphere, which, so it's already tested. We do have it working in vacuum. We do have limited success of doing it also with particles. There are still some challenges, but yeah, I'm happy to answer any of the questions regarding this. So this is my last slide. Thank you.
Okay, Alex. Yeah, can you? Okay, I'll get you the microphone.
Yeah, thanks for the great talk. Do you have any plans to address load balancing in entity?
There is no plans at this point. The hope is that by choosing the correct grid, in particular in spherical, you can choose, you can squish the grid in theta, you can squish the things in R, and it's actually adaptive, so you can actually change that. And same for the cubed sphere. In cubed sphere, you can also have radially stacked at different scales. So the hope is that that should accommodate most of it. Per se, there is no plan to do that, but if there is a necessity, we've done that in previous codes and Tristan v2, so it's not very hard.
Thank you. Thank you, Hayk, for the great talk. Very interesting. You call this, so entity is the peak code for plasma astrophysics, as you wrote over there, right?
Yes.
But as you said earlier, there's been, there are quite advanced peak codes, including with radiation and QED in the laser plasma community. I'm wondering whether either this code can be used for laser plasma problems, or whether there's been any sort of intellectual exchange. Have you borrowed anything from codes like Osiris or Epoch or Smiley? What's kind of, how does it compare with that, for example?
Right, so I think the main, so to answer your second question, whether there is any exchange in experience, the answer is yes, there are quite a lot, not in the entity particular, but in, for instance, in the QED module of the Tristan v2, parts of it, or there is an algorithm which resamples particles, particle merging. So both of these have been borrowed from algorithms developed by people who worked on Osiris, for instance. As to your first question, whether you can use this, I would be very cautious because there is a lot I don't know. Simply don't know. There is probably a lot of the requirements that are, needed for specificities that are needed for simulating these environments that are not directly translatable into some advanced boundary conditions or I don't know. So I'll be happy to learn. I mean, you can do that.
Some basic problems that
you can do that. But again, I'm not ready to say that, yes, you can just pick up the code and run it. I'm just not qualified enough to, to go in that direction.
Hi, thank you for the talk. You mentioned that users take this code and it is their code. It's very generous of you. Do you have any strategy of making sure that you don't have 600 entities after a few months? Because what people do is they take your code, it becomes their code, they never check it back in, and then you have 600 versions of entity, and they never update, and old bugs stay unfixed for years.
Yes, the answer is we explicitly develop and explicitly keep up to date the version. So if there is a bug which is found later, and you have some, for your version of the code, that bug is never going to be fixed. So in other words, there is a main version which we're responsible for, so it's money back guarantee and everything. But if you're branched out and suddenly there is a feature that we added in the main version of or there is something else, people are free to fork it, make it private, and develop their own modules. I can't control that. But in practice, basically it's a soft power approach. So you try to make it as usable as possible so that if someone breaks it in a different branch, it's not the problem of the main developers.
Yeah. Yes.
I know. It's BSD3. It's pretty common open source license, but apart from license, we also have a code of conduct which explicitly prohibits any of the developers from claiming, that it's their code. So you're welcome to acknowledge the code. You're welcome to, include any of the people who helped you in using the code and, grant proposals, etc. I get emails, for instance, of we applied for a grant with this code. Can your code do this? Well, maybe you should have asked before, because maybe the capability is just not there yet. So in other words, people do use the code without our knowledge, and I'm quite proud of that. That helps also with my sanity, so that you don't have to diverge too much into helping people. But that's the point. You're developing you're making code accessible from the first try.
I've got a question that's maybe a little technical, just to make sure I understood correctly. So when you were talking about adding the ions in to the reconnection stuff,
yes.
You said that they wouldn't radiate, but they had a mass ratio equal to 1.
Right.
So they're just not radiating because it's just not in the algorithm to say that they radiate?
Yes, so the actual synchrotron drag itself, the radiative drag, is not resolved on the grid. So you have to add an additional, it's called Landau-Lifshitz force, basically, as an additional drag term to the equations, the equations of motion. So you just don't add that for a given species. It's just turned off, yeah.
Yeah, we have one question right there in the back. No. That's good.
Sorry, maybe this is overly technical, Hayk, but when you have this stitching of the mesh, I was wondering if you have any problems with the particles crossing the stitching regions, because like people who have worked on this before, like Jean-Luc Bay in AMRX,
they didn't work on this.
No, I know. No, what people who have worked on
self forces,
refined meshes, exactly.
That's different. So in if I understood correctly, it's a great question. So the reason we don't have AMR in PIG, part of the reason is that when your particle crosses from, say, 1 resolution to twice larger the resolution, what was discovered is there is a self force, which there are ways to mitigate it. In this case, you're not really crossing, the sizes of cells are equal in a way. We haven't, to be fair, we haven't explicitly measured whether there is self force. So right now, all the sort of testing is just you're looking at the flat space-time and comparing it with this. So if there is no difference, then it's probably fine. But it's a fair question. Still a lot of work to do here. So.
Yeah, just one quick question. So what does this couple with other tools from numerical relativity, like the Einstein toolkit to generate grids and all that? How is
No.
this? Are there plans for this? Because this would be
If there
kind of
is-
a natural development, right?
If there is necessity, yes. My impression was that sets of problems modeled by Einstein toolkit are mostly about very dense environments around, mergers, say. Which, I mean, I don't want to say there are no PIC problems there, but it's definitely not the first thing I would do.
Yeah, I was thinking about how you generate the meshes and all that. With all
Mesh is it's basically a metric file. It's a file with a collection of metric elements. That's it. Yeah.
Okay, so lots of things to think
Thank
about
you.
and discuss. Okay, thank you very much, Hayk. Thank you.